Okay, now we are going to have an example to examine this odd and even functions that we have and see how it will simplify our calculations. We will compute the Fourier series of f of x equal to x. Okay, so our function here is f of x equal x. Okay, on the interval minus pi to pi. Okay, so in this case we are going to have first, this is what? This is odd function, right? This is odd function. So because x cosine nx is an odd function on this interval, do you remember that we are going to have here f of x cosine x in order to obtain an? So we found that this is odd function times even function, so it is going to be what? Exactly odd function. So the integral here is going to be exactly 0. And based on this, this coefficient is going to vanish, and the remaining one is going to be bn only. So we are going to calculate, okay, we're going to calculate the bn coefficient only. Okay, this means that an is going to be 0, as we said, and we need only to compute pn. So no need to compute an at all. So we are going to have our computation here 1 over pi, because 1 over L from minus pi to pi, from minus L to L, x sine nx. Okay, x here, this is the function, times sine nx, which is n pi x over L. So we have here our n times x, right? Because we have L equal to pi, right, in our case, because this is the interval here from minus L to L. Then we are going to say confidently that we have, this is odd function times odd function, then they are going to give us even function. So the integration is going to be double of the integration from 0 to pi of x sine nx. This is a simple limited integration. We can obtain it, integration by parts, and we are going to obtain that 2 over n squared pi sine nx minus 2x over n pi cosine nx from 0 to pi. If we substitute here in this in these two terms in order to obtain the final integration, we are going to end up with minus 2 over n times cosine n pi, and we said that it equals to exactly minus 1 to the power n. And we have another minus here, so we are going to add another one here. Okay, so it is going to be minus 1 raised to the power n plus 1. And 2 over n, it is going to be like the constant here. Okay, so the Fourier series of x on the interval minus pi to pi is going to be the summation of 2 over n minus 1 raised to the power n plus 1. I said this is the part here, times sine nx, right? This is the Fourier series for this part, which is the part having the sine only, right? And this is going to be from n equal to 1 to infinity, of course, for any number that we want it. Okay, the next part, which is related to the convergence. Okay, we want to know what is the convergence of this function actually is. So the convergence, this function, this converges to x for the interval from minus pi to pi, and it is going to converge to 0 at the ends or the limits of the interval, which is minus or plus pi. If you remember, you want to remember theorem 13.1. Do you remember this? So I'm going to show it to you here quickly. This is what I have explained like 2 or 3 videos before. So if we're talking about inside the interval minus L to L Fourier series, if it's piecewise smooth, of course, so we are talking about the convergence within the function. It is going to be half f of x from right plus f of x from left. Okay, this means that we are going to have f of x in our case. At the end minus L and L, this Fourier series converges to half f of L from left plus f of minus L from right, and then we can calculate it. This is at the intervals, right? So in our case, we have here at because we have like at x equal to pi and at x equal to minus pi, they are going to have like the same values with different, the same magnitude with different signs. So we're going to shift to 0. Okay, let's see the figure to see how this Fourier series are going to be representing our function. Look here, this is the function here. So actually this is the Fourier series, as you can see it here. Okay, this is the Fourier series of this function as if that we are having odd function here because it's reflected on 0. So at any point we are going to find that from left and from right the function Fourier series seems to be converging to the function itself, f of x. However, when we go to L or minus L, okay, which is pi here or minus pi here, okay, so we're going to find that it converges to what here, as you can see? Yes, exactly, converges to 0 here and 0 here. Okay, why? Because we have half times. Here we are converging, we are almost having f of x. If we are going to have the function is converging from the right and from the left to values that is equal in magnitude and different in signs. So we're going to find that at the end we are going to have 0, which is this function, this value. And remember, this is our equation that we are going to use. Okay, L from left and minus L from the right. Okay, so this is going to be our case. So minus L and L are going to give us, the functions are going to have, as I said, equal magnitude but different signs, and based on this we are having 0 as a convergence of this function. Okay, this is the 20th partial sum of the series in our example. Okay, so this is an important issue and you need to think about this. Remember that this is what, as I said, it is odd function. So we are expecting that it is going to be something like this, right? And the Fourier series is going to be something like, as I said, something like this, right? So it is odd function and as we are expecting. Okay, now let's go to another example and finish this part which is related to odd and even function. So in this example we will write Fourier series of x raised to the power 4 on the interval -1 to 1. Okay, so this x raised to the power 4 sine n pi x over L here is 1, so it is okay, n pi x only, is an odd function because this is odd function, this is what? Even function. So the multiplication would give us what? Odd function. On this interval, for n equal to 1, 2, 3, and for each Pn equal to 0. Okay. Okay, so the point here, because we are sure now that it is odd function, this multiplication. So remember that this is Bn in our Fourier series. So we have the multiplication here is going to be odd, then this term is going to be 0 and Bn is going to be exactly B0. So we are going to calculate exactly A node and An. A node, it's the constant term, you remember? Like so, A node it equals to 1 over L from minus L to L f of x dx, right? So now because f of x in itself is what? Even, right? So in the even function we are going to use double of the integration from half of the interval from 0 to 1 instead of -1 to 1. X to the raised to the power 4 dx. If you make this simple integration, you're going to find that it gives you the constant term in our Fourier series function. It is 2 over 5. Now this is the first fixed term. Now let's go to the term An, which is related to the cosine terms. So we said that here f of x even times even times even, it would give us what? Exactly even. So our integration is going to be double the integration from 0 to 1 of the function f of x times cosine n pi x over L, which is 1. Okay, so n pi x. If we're going to make this integration, we're going to find 2 as it is, and then integration by parts. We're going to find like one term here plus another term here, both of them divided by n pi raised to the power 5. Okay, this term, it has sine n pi x, this term has cosine n pi x. Okay, then we are going to substitute with the limits 0 and 1 in this big fraction here, and we are going to end up with this long fraction here. You can check it by yourself if you want, and then you are going to find that you have this long these 3 terms on the denominator, and the numerator is going to be the same. Based on that, you are going to end up with 8n squared pi squared minus 6 over n to the raised to the power 4 and pi 4 times minus 1 n. This is how this series is going to be ended with. So the Fourier series is going to be first exactly the fixed term here. It is 2 over 5, but remember we multiply by half. Okay, so half goes with this 2, then the remaining is 1/2 here, and then the remaining, the second term is going to be from n to 1, n equal to 1 to infinity, and here between parentheses our term that we have obtained already here, this is right. Okay, it's the same after just rearrangement of it, times cosine n pi x, as I said, n pi x over L. This is what we are having here in our equation for the Fourier series. Okay, so now what we are waiting for is to see the Fourier series. Okay, so by theorem 13.1, do you remember theorem 13.1? Again, I have repeated it many times. Convergence of Fourier series, if it's piecewise smooth between minus L and L, so in this interval, the convergence is half f of x from right plus f of x from left. Okay, as we said, at any point here or here, are going to find that from left and right. Okay, I mean that this is from right and left. I mean, okay, so it converges to the function itself. So if we assume that, if we assume that, exaggerating, this is like Fourier series, so you're going to find that it converges to the point on the function itself, on the curve itself. Okay, let's clean this. Okay, and at the end we are going to find that at both minus L and L, this is here minus L, and here this is L at minus 1 and 1, we are going, this Fourier series converges to exactly half f of L from the left. Okay, f of L, where is L here? This is L. This is L. From the left means that here, as we are coming here, so it converges to, as if that we are ending here, for example, it is x raised to the power 4. Okay, so it is 1 raised to the power 4 equal to 1. So it converges to 1 here. Not converging, this is the value of the function here from the left. And this one is what? From here. It is going to be x raised to the power 4, and this x, in this case, it's going to be minus 1 raised to the power 4, which is going to be 1 also, right? So we are going to end up with another 1 here. So this is 1, this is 1, right? Okay, so this is 1 plus 1 times half, so it equals to 1. So means that they are going to converge to 1, and this is true, as you can see it here. Let's clean. So it is here. They are converging to, both of them, they are converging to 1 here. Okay, so by theorem 13.1, the series converges to x to the power 4 for x between minus 1 and 1, as we said, and this figure shows the 20th partial sum of this series. 20th means that we have taken 20 terms from the Fourier series. As you can see, it is highly smooth, almost it is representing our function. And this is the magic of using Fourier series, that using the cosine terms or sine and cosine terms, you can obtain a very smooth like function of our original function, okay, compared with the function. Now we know everything and know how it converges at any point and how it converges at the ends, and everything is okay, and we got the benefit already from using odd and even function. Okay, this is the end of this video, and I hope that you understood it well, and see you in the next one.